A state-of-the-art language model can score like 74% on complex Harvard-level mathematical reasoning benchmarks. But if you drop that exact same model into a virtual household environment and just ask it to put an apple in the fridge, it fails completely. Welcome to AI Paper Slop.
Yeah, the disconnect is just wild.
It really is. Today, we are looking at a brand new paper from researchers at Peking University. It's called Adapting the Interface, Not the Model: Runtime Harness Adaptation for Deterministic LLM Agents. And if you are an ML engineer building agents today, we are jumping straight into the core insight. So what is the fundamental takeaway from this research?
Well, the core takeaway is that the standard industry paradigm for improving LLM agents is, it's just fundamentally flawed when applied to deterministic environments.
Flawed how? Like, what are we doing wrong?
So if your agent is failing at web shopping or, database querying or operating system control, your first instinct is almost certainly to update the model weights.
Right, like using supervised fine-tuning or RL or maybe some distillation.
Exactly. You try to fix the brain. But this paper argues that in rule-governed domains, failures are rarely reasoning errors. They are actually interface mismatches.
Interface mismatches. Okay, so how do they fix that?
The authors introduce something called Life Harness. It's this highly dynamic 4-layer runtime interface that sits between a completely frozen language model and the environment.
Totally frozen, so no weight updates at all?
None. 0 parameter updates. They basically use an AI coding agent to write and evolve this software harness based on failure trajectories rather than tweaking the LLM itself. And doing just that, they achieved an 88.5% average relative performance gain.
Wait, 88.5%?
Yeah, across 18 different models, all without updating a single neural network parameter.
Okay, that 88.5% gain with 0 parameter updates, that challenges the entire premise of how we currently train agents.
It really does. It flips the whole script.
Right, so before we get into the actual architecture of this life harness, we really need to understand the diagnosis of the problem. If a model can do complex math, like we said, but fails at navigating a simulated kitchen, why is a fine-tuning job the wrong approach to fix it?
Well, it requires looking closely at the fundamental equation of what an agent actually is. I think we have a tendency to conflate the language model with the agent, but an agent equals the model plus the environment.
Right, they're two separate pieces of the puzzle.
Exactly. And in a deterministic domain, like, say, interacting with a strict API for flight bookings or executing bash commands in an OS terminal, the constraints of that domain live entirely outside the model.
Okay, so you mean things like API formats, available tools, strict stopping conditions?
Yeah, exactly. Those are external, rigid rules. They don't belong in the model's latent space.
So the model is basically being evaluated on its ability to play by the environment's specific syntax rules, rather than its raw, underlying reasoning power.
You hit the nail on the head. And the researchers proved this by doing this manual, highly detailed analysis of 393 failed episodes across their training environments.
Oh, wow. They manually analyzed almost 400 failures.
Yeah, painstakingly. They specifically looked at Quen 3.54b. And the breakdown of those failures is incredibly telling. Out of all those errors, only 9.9% were actual general reasoning errors.
Wait, less than 10%?
Less than 10%.
So over 90% of the time, the model actually understands the goal and formulates the right tactical intent, but it just, crashes on execution.
Yes, exactly. The vast majority are just interface bottlenecks, and they categorize these into 3 specific modes. First, you have action realization failures, which made up about 23.2%.
What does that look like in practice?
That's when the model has the right intent, but outputs the wrong format. So it writes a natural lineage command instead of a strict JSON tool call, or, it just misses a required trailing comma.
Oh, classic JSON errors. That's brutal.
Right. And second, environment contract failures accounted for 33.3%. This happens when the action is perfectly executable, the JSON parse is totally fine, but the model fundamentally misunderstood the tool's boundary condition.
Like trying to do something the tool technically allows syntactically, but the environment says is illegal.
Exactly. And finally, trajectory degeneration, which was 33.6%. This is your classic infinite loop.
Oh, I've seen that, where the agent gets stuck trying the same invalid action over and over.
Yeah, just exhausting its context window and token budget without making any actual progress.
It's like trying to teach a brilliant theoretical physicist how to play a new tabletop board game by doing invasive neurosurgery on them.
I love that analogy. Yeah, invasive neurosurgery.
when all you actually need to do is rewrite the rule book so it's formatted in a way they can easily digest.
Right, just give them a better user interface and a clear reference sheet so they don't place their pieces on the wrong squares.
Exactly, because when you use parameter adaptation, like fine-tuning the weights, you are essentially forcing the model to memorize the board game's rulebook internally. It absorbs all those external domain constraints into its neural weights.
And those constraints are stable external properties of the environment. I mean, think about it. If the model outputs a perfectly reasoned choice, but forgets a single backtick in a SQL query.
The environment just returns a generic syntax error.
Exactly. And then the model spirals. Fine-tuning attempts to optimize the weights to remember that specific backtick. But the researchers argue, why do that? Just intercept the output, fix the backtick in the software harness, and let the model focus purely on the reasoning.
Which makes total sense. And that brings us to the actual mechanics of how this is implemented. If fine-tuning is completely off the table, how do we rewrite this rulebook dynamically? Because, I mean, you can't just append a massive static system prompt that eats up the entire context window.
Right, that would be incredibly inefficient.
So we know the architecture has 4 layers. Let's look at how it patches these misunderstandings before the execution even happens. Walk me through the first layer.
Okay, so the first defense is the environment contract layer. Its job is to calibrate the tools dynamically.
Give me an example of what that looks like.
Sure. In the airline benchmark, which simulates a flight booking system, agents frequently mess up cancellations. They try to cancel flights that have already taken off.
Oh, obviously you can't do that.
Right. So the contract layer dynamically patches the tool description injected into the prompt. It explicitly adds a rule, literally saying the cancellation tool transfers flying or landed flights to a human agent, and you must check these 4 specific cancellation conditions first.
Oh, I see. So it's injecting like pre-flight checks into the prompt to constrain how the tool is used right then and there. But what about the specific syntax requirements of the tool itself? How are we handling those procedural quirks? Because if we inject a massive list of syntax rules for every possible tool, we are going to dilute the primary instruction and blow through our token limits anyway.
And that's exactly where the procedural skill layer comes in. It handles task conditioning using a highly targeted retrieval mechanism.
Oh, so it's pulling in context on the fly.
Yes. The researchers extracted a library of reusable successful skills from the training data. When a new task comes in, this layer uses BM25 retrieval to pull only the most relevant skills.
Wait, BM25. Why BM25 instead of dense vector embeddings? Usually, modern retrieval systems default to semantic search.
It's a great question, because in deterministic programming environments, exact keyword overlap is often far more reliable than semantic similarity.
Ah, because the syntax is so rigid.
Right. If the task involves a specific MySQL error code or a very specific API endpoint, BM25 matches those distinct tokens perfectly. Semantic search might give you something conceptually similar, but programmatically useless.
That makes a lot of sense.
Yeah. So for example, in DBbench, the model might be asked a database manipulation question. The skill layer retrieves concrete, non-parametric reminders, like telling the model to use backticks for MySQL identifiers, or specifically how to handle NUL values in that exact dialect.
So it just injects the necessary code snippets for that specific step, keeping the context window incredibly lean.
Exactly.
Okay, so we've conditioned the input. The model knows the tool boundaries. It has the right syntax cheat sheet. It does its reasoning and decides to take an action. But, I mean, the model still has to output executable strings. What stops it from hallucinating a malformed bash command and just crashing the terminal?
Well, that is handled by the third piece, the action realization layer. You can think of this layer as the bouncer at the club.
The bouncer, I like that.
Yeah, it intercepts the model's action before the environment ever sees it.
Okay, so it intercepts the action, and if it's malformed.
It canonicalizes it or blocks it entirely, returning a targeted error directly back to the model.
Oh, instead of letting a bash terminal return a generic confusing error that derails the model's reasoning.
Precisely. The bouncer rescues the command. If it's a simple syntax issue, like, say, fixing a missing parenthesis in a JSON payload, it just patches it silently.
That's brilliant.
But if it's a dangerous shell pattern or it's structurally invalid, it blocks the execution and returns a model-visible error message. And that message explains exactly why it was blocked based on the harness rules.
But wait, let me push back a little here. Prompt optimizers like Opro or GPO, They actually change the system prompt iteratively to avoid these kinds of errors. If life harness is just intercepting and blocking a bad action, isn't it still ultimately relying on a text prompt to tell the model why it was blocked?
I see where you're going with that.
Like, as an ML engineer, how is this really different from just advanced prompt engineering?
It's a crucial distinction, actually. Frameworks like OpenIO optimize static text, right? They rewrite instructions or templates in the hopes that the model gets it right on the first pass.
Right.
Life Harness is active, dynamic runtime code execution. It is running actual Python scripts that actively parse states, validate rejects, track token budgets, and manage the multi-step execution loop completely independent of the LLM.
Oh, so it's actual software middleware mediating the state transitions, not just a clever textual prefix.
Exactly, it's real code. And the paper actually includes a direct ablation study comparing Life Harness against those exact state-of-the-art prompt evolving methods.
And how did it do?
Life Harness achieved a 120% average relative improvement over prompt-only optimizers.
Wow, 120%.
Yeah, because textual prompts can only do so much, you know? A static prompt to not dynamically catch a bad JSON payload at step 15, parse the exact missing key, and reconstruct the payload before the API crashes.
Right, because it's static. It can't react in real time.
Exactly. Because Life Harness mediates the dynamic feedback loop via code, it captures structural issues that a static prompt simply cannot touch.
Okay, that makes perfect sense for single-step errors. But what about the trajectory to generation, the infinite loops we talked about earlier? Anyone who has built an agent has watched it endlessly click the same unclickable button on a web page until the context limit is reached.
It's the most frustrating thing to watch.
It really is.
Yeah.
So how does code middleware solve a temporal reasoning failure like that?
That requires the fourth component, the trajectory regulation layer. This operates after the environment executes the action and returns feedback. It maintains a full state machine of the entire episode history to detect stagnation.
Okay, so it has memory.
Right. In ALF world, models notoriously get stuck in these examine without lamp loops. They keep trying to examine an object in a dark room, the environment says it's too dark, and the model just tries examining it again.
Because it lacks the long horizon memory to realize it's been doing the exact same thing for 10 steps?
Yeah. Right, so the trajectory regulation layer tracks these repeating n-grams of actions and feedback. When it detects a cycle, it forces a soft recovery message or even a hard structural directive, explicitly breaking the agent out of the loop.
So it effectively acts as an external prefrontal cortex. It's monitoring the agent's progress and saying, hey, you've tried this 3 times, the loop is broken, transition to a search strategy.
Exactly. It forces the pivot.
Okay, this architecture sounds incredibly robust. We have the contract layer, the skill retriever, the bouncer validating inputs, and the loop monitor tracking history. But this brings up a massive logistical bottleneck.
Which is?
Writing the rejects, the API validators, the custom state machines, manually coding that for every new environment just does not scale. If you are deploying agents across 50 different APIs, writing a custom middleware harness for each one is a nightmare.
Oh, absolutely. And researchers completely agree. The true innovation of this paper isn't just the architecture of the 4 layers, it's the evolution mechanism.
Evolution mechanism.
Yeah, they automate the creation of this middleware using an AI coding agent, specifically OpenAI's Codex.
Wait, so we have an AI writing the middleware for another AI agent.
Exactly.
Okay, walk us through how that offline workflow actually functions.
So they execute an offline evolution process. First, they take a frozen Qwen 3 4B instruct model and run it on a set of training tasks to generate interaction trajectories.
And naturally, because the environment is strict, the model fails on many of them.
Exactly. It generates a bunch of failure traces. They then feed these traces into Codex.
But what exactly does Codex see in its prompt? Is it just looking at the raw terminal logs?
Not just the logs. Codex basically acts as a diagnostic software engineer doing test-driven development. It is provided with the trace, the environment error, and the specific architecture of the 4 harness layers.
Okay, so it knows the structure it's supposed to be writing for.
Right. It reads the traces, identifies the recurring patterns causing the failure, and literally writes Python code updates to the appropriate layer of the harness to prevent that specific failure in the future.
But how does Codex manage the version control of this harness? What if Codex writes a buggy loop breaker that just crashes the middleware entirely? We all know code generation models hallucinate logic too.
Oh, for sure. That's why they implement an evolutionary verification step. Codex proposes a patch to the harness code. The system immediately evaluates this new patched harness against a validation set of trajectories.
So it tests it instantly.
Instantly. If the patched harness causes regressions or crashes, the feedback is routed back to Codex with the Python traceback, and Codex refines the code. Only patches that strictly improve the success rate are actually committed to the harness repository.
Wow. It really is like a sports team reviewing game tape. You know, the players on the field of the LLM, they keep running the same play and missing the block.
And instead of sending the players back to training camp to fundamentally change their physical attributes, which would be fine-tuning the model,
The coach, which is Codex in this case, watches the tape. The coach realizes the players are fine, but the playbook is confusing, and the field markings are ambiguous. So the coach just updates the playbook and paints new lines on the field for the next game.
that is precisely what is happening. And the empirical data backs up just how efficient that coaching is. If you look at Figure 6 in the paper, which tracks the evolution dynamics, the training set performance converges remarkably fast.
Like, how fast?
It doesn't take thousands of iterations. The performance improves steadily over just a few evolutionary cycles and then completely saturates.
A rapid saturation implies that the failure modes in deterministic environments aren't a long tail of unpredictable hallucinations, right?
Yeah.
They are systematic, highly concentrated mismatches.
Exactly.
So once Codex writes a targeted interface update, say a regex to fix a specific SQL dialect issue or a state tracker for a specific API error, that entire class of failure is practically eliminated.
Yeah.
You don't need a massive data set or 10,000 GPU hours of fine-tuning to fix it. You just needed 20 lines of Python in the runtime layer.
Right. It's computationally cheap and highly targeted.
But this leads to the most critical question for deployment. We've got Codex watching tape of one specific team, right? The Qwen 3.4b model. Codex writes a highly optimized custom middleware for that team in that specific environment.
Correct.
Does this customized playbook overfit to the quirks of that one Qwen model? Or does the harness generalize? Like, if I swap the model out for a larger parameter model, do I have to re-evolve the entire harness from scratch?
This is perhaps the most significant finding in the entire paper. They took the exact harness evolved entirely on Qwen 3.4b instruct trajectories, froze the Python code, and then applied it to 17 entirely different model backbones.
Wait, we're talking models outside the Qwen family.
Yes, entirely different architectures and training distributions. They tested it on Llama 3.1 and 3.3, DeepSeek models, various sizes of Qwen 2.5, and XLAM.
And what happened?
Across all those models and environments applying the same, Qwen evolved harness improved performance in 116 out of 126 settings.
116 out of 126. That's a 92% hit rate for a software harness that never even saw those models during its evolution phase.
Yeah, it's incredible.
I mean, that proves the harness is capturing the stable environment-side structure, not compensating for model-specific behavioral quirks. The rules of the operating system, the constraints of the web shopping API, these are universal realities. A mathematically sound interface helps any capable reasoning engine navigate them.
Precisely. The harness maps the environment, not the model.
But let's dig into the XLAM comparison, because that is where this gets truly disruptive for ML research. For those who aren't familiar, XLAM is a family of models specifically fine-tuned for agentic tool use.
Right, highly specialized.
Researchers spent massive compute cycles rewiring the internal weights of these models, specifically so they would be good at interacting with these kinds of rigid environments. Surely a model whose actual neural weights have been trained for tool use beats a generalized reasoning model that is just using a runtime harness.
You would certainly expect that to be the case. But the researchers ran a direct comparison. They took the base generalized model, Qwen 2.532b, and they compared it against XLAM 232b FCR.
Okay, so the base model versus the specialized one.
Right. And that XLAM model was specialized directly from that exact same Qwen base model specifically for tool use. On the TauBench benchmark, which is an in-domain environment for the XLAM training data base, generalized Qwen model operating with the life harness actually outperformed the specialized XLAM model operating without the harness.
Are you serious?
Yeah.
The vanilla model running the Codex-written middleware beat the model whose brain was explicitly rewired via fine-tuning for that exact task.
Yes, and the implications get even worse for the specialized model.
How so?
When they tested both models on out-of-domain tasks environments, the XLAM model wasn't explicitly trained on, like task-aware bench and agent bench, the XLAM model actually degraded. It performed worse than its own vanilla base model.
Wait, why does fine-tuning cause out-of-domain degradation here? Is it like catastrophic forgetting?
It's an extreme case of overfitting to the training distribution's interface. When you fine-tune for deterministic tool use, the model absorbs the specific API schemas of the training environment directly into its internal weights.
Oh, so it memorizes the exact syntax and feedback loops it saw during training.
Exactly. So when you drop it into a new environment where the schema shifts slightly, those rigid, hard-coded weight assumptions break. It hallucinates parameters or expects a JSON structure that just no longer applies.
So the parameter training actually hurt its ability to generalize to new environments. By trying to bake the rules of the environment into the weights, we make the model brittle. But the harness approach avoids that entirely.
Yes, because the harness keeps the domain constraints completely separate from the neural weights. The language model remains a pure generalized reasoning engine. Interestingly, when the researchers took that specialized brittle XLAM model and applied the life harness to it, its out-of-domain performance shot back up.
Oh, wow. So the middleware basically rescued the specialized model from its own parameter brittleness.
Exactly, by acting as a buffer between its hard-coded assumptions and the new environment.
You know, if you are an ML researcher or an engineer building autonomous agents today, the core takeaway is just incredibly clear. Stop burning expensive GPU compute trying to retrain your model's weights to memorize the rules of stable environments.
Yeah, it's a trap.
Parameter adaptation absorbs domain constraints into the weights, which makes your agents brittle and incredibly expensive to update when the environment changes. Runtime adaptation maps the stable structure of the environment into reusable model-agnostic code.
Right.
If your environment is deterministic, if the API has strict rules, if the database requires specific syntax, build a better harness, evolve the interface automatically using a coding agent, and let your core language model do what it does best, reason over the latent space.
It is a profound shift from model-centric optimization to interface-centric engineering. As the harness evolves to handle all the syntactical and procedural overhead, the language model effectively becomes a clean compiler for natural language intent.
It really leaves you with a wild, almost counterintuitive thought about where this is all heading. We have spent the last few years assuming that to get closer to AGI, we just need to keep building larger, more omnipotent neural networks that internalize every piece of domain logic in the world.
Right, the mega model approach.
Exactly. But if the runtime harness is doing all the heavy lifting for loop breaking, skill retrieval, and syntax validation, maybe the future of autonomous AI isn't one massive trillion parameter omni model. Maybe the future looks like tiny, cheap, completely frozen reasoning models running inside incredibly complex million-line software harnesses written entirely by other AIs.
It fundamentally changes the definition of where the agent actually lives in the stack. Is it the model or is it the harness?
A fascinating shift in the landscape for sure. Thank you all for joining us on this deep dive into the architecture. We will see you next time on AI Paper Slop.